Welcome to the office. We want to take a look at the theorem of Lagrange. All right, so let's take a look at our notes here. The theorem of Lagrange states simply, if we have some subgroup of a finite group G, we have that the order of the subgroup is a divisor of the order of G. So if the order of G is equal to n, and the order of H is equal to m, for example, then n may be written as a multiple of m. Okay, that's essentially what we're saying here. A couple of different ways that we can look at it. Maybe you want to say that n divided by m is an integer. That's okay too, right? A few different ways to consider this. We want to observe this through a couple of things that we've already stated. So essentially, I'm giving an outline of the proof here. So recall that we have this equivalence relation. Okay, so we recall that we have this equivalence relation. Let's see here, is an equivalence relation. And what does that do for us? Well, it has with equivalence classes being the cosets of H, whatever the subgroup happens to be that we're using. So we have an equivalence relation which is based off of some subgroup. An equivalence relation will give rise to equivalence classes. The equivalence classes in this case are cosets of H. However, equivalence classes define a partition of our set G. And if we have a partition of the set G, then we can add up, right? We can add up all of the elements in the individual equivalence classes to find the total number of elements in G. This works because G is finite, therefore the equivalence classes are finite. All right, so equivalence classes define a partition of G. Excellent. So we have this idea, we have this idea. If we define phi to go from H into AH by phi of, let's see here, I want H and move into AH by multiplying on the left by A. Excellent. So if we define this, we want to notice that phi is a bijection. We know that it's a bijection because, let's see here, if it weren't one-to-one, then it would be, we would end up having two identities, essentially, is the problem. So it's one-to-one, that's pretty clear. And then the co-domain of our function phi is essentially defined as the image of the domain. So trivially, it's onto, because it's defined to be the set of things that we get out of this function. So pretty clearly, anyway, it is a bijection. Hence, the number of elements in H is equal to the number of elements in AH for all A in G, which means that all of our cosets, all of our equivalence classes are the same size. Okay, so we are formally saying it here through the bijection. So if we let the size of H be equal to m, the size of G, the order of H, the order of G, be n, and say there are R cosets, then the number of elements, sure, the number of elements in the entire set can be observed as the size of A1H plus the size of A2H, right? All of these left cosets, all the way up to A sub RH. These are distinct cosets here. So I'm just looking at the collection of distinct cosets. But each of these cosets has the same size as H itself, which is m. M plus m plus all the way up to m. That is R copies of m, which is just R times m. Now, if I write it a little bit more explicitly, that is, the order of G is a multiple of the order of H. Or, again rephrased, that is, the order of H divides the order of G. And that's exactly what Lagrange's theorem says. So these are all the details that we need in order to prove Lagrange's theorem. Essentially, the only thing this is lacking is maybe a few details and the nice format of a proof. But this is everything that we need to be able to observe and verify that Lagrange's theorem is true. So fantastic. This is pretty cool. Pretty cool stuff. We'll take a look at a couple of theorems, which we will simply observe relatively quickly as results of Lagrange's theorem. So join me back here in the office for those couple of theorems in just a moment.